And then we're going to be going over the third lab today. So we're going to be basically going through the VKS walkthrough, and then we'll go over the data reduction for that too. So first memo, the average for that, for people that turned it in, because there was a few that didn't turn it in. And if you're in the class right now, if you're in this Zoom meeting and you didn't turn in the first memo, reach out to me so I know why you didn't turn it in. If you had some kind of personal issue that prevented you from turning it in, then let me know, because I want to be sure that all of you, get all of the points that you can get. But for those that turned it in, the average was an 84, so that's, it's a good average, but it's also honestly a little higher than usual, and that's only because the first memo I usually grade a bit easier overall, but I guess not. I'm not going to grade like really hard after this, of course, but this is probably going to be a higher average than usual, at least by a bit. So if you haven't looked at the feedback yet, you want to really make sure that you take a look at that, and I'll show you how to look at it if you don't know how. So to look at the feedback, you're going to go to assignments. You're going to click on experiment 1. And then you'll go up to the top here to submission details. So, for me, I'm just in this kind of mock test student kind of thing, so it doesn't show any submission here. But if you click on submission details, then you should see my feedback. It should be on the right hand side. I kind of have a rubric for this, well, for every submission that you have, and you should see that I have some comments in that rubric for each of your submissions. So really make sure to look at that feedback. I try to give you a lot of feedback for each memo, but especially for the first one, so you can kind of look at that and then take that feedback and implement it in all of the other memos that you have. Alright, so especially for things like the abstract, I don't think many of you have either ever written an abstract, or maybe you've only written a few of them. So look at the feedback for that. But overall, it's pretty good, so I'm glad. But yeah, make sure you look at that feedback. And then memo 2 that's due today. So if you've already turned in memo 2 and you didn't look at the feedback, I would really recommend that you look at my feedback and do any adjustments that you have to make, and then you can resubmit memo 2 before the deadline tonight. I know a few of you have already turned it in, so I'm not going to grade any of them until the deadline. Alright. And let's see, what else do we have? Oh yeah, are there any questions on the first memo for, I don't know, grades or anything, or memo 2 that's due tonight?
So when I was trying to calculate the strain of the material, I would compare it to the strain that the resistance gauge collected, and it was a little bit off. Was the gauge length different, or is this resistance gauge kind of a little off from what we might calculate anyway?
Yeah, the gauge length is going to be the same for how, if you have the strain gauge, that's getting the strain directly. So you don't need to worry about the gauge length or anything like that. The strain that you get with the strain gauge and the strain that you calculate from the extensometer, they should be similar. They're going to be a bit off. I'll show you what the graph should look like. So I'm going to pull up basically just a past student's memo. They're not perfect graphs, to be honest, and it looked like from the data that we had for this memo, it's not great data, to be honest. But let me pull up a past student's lab. So your graph should look something like this. So this graph here is actually pretty good. They're pretty close. But other graphs, they're going to look like this, or you see here it deviates quite a lot. So your graph should look similar to this. Of course, not exact, but yeah, basically the strain or the stress strain curve that you have with the strain gauge and the extensometer, they're going to be not great, to be honest. So it should look something like this though. So if you have any issues though, be sure to go in the Discord before the due date tonight. Okay. Anything else?
Professor, do we have to get the elastic modulus for all 3 diameters, or just like a sample one for the first diameter?
It should be, you should be able to just use one calculation basically to get the elastic modulus. Actually, you're not calculating the elastic modulus, that's going to be given. So, you're using the same elastic modulus for all of your graphs.
Thank you.
Mm-hmm. All right. Anything else? Okay. Also, if your graphs here are really off, don't forget that you have to convert to the strain gauge, the units for that, because that was first in microstrain. So you have to kind of convert those units to, or I guess the scale, to have consistent units with the extensometer. So your graph should look something like this. Also, you see here there's a legend. I don't know if we went over that in the first data reduction that we did as a class, so I'll show you guys how to make a legend as well. So we'll do that. I'm going to start out with that, and then we're going to go through the third experiment. Okay, let me share my screen again. Go over here.
I had a quick question.
Mm-hmm.
For the elastic modulus, are we supposed to calculate one elastic modulus for each of the, I guess, the experiments?
You don't need to calculate the elastic modulus. That's given.
Oh, I did not see it on the data given.
It might not be on the handout, so it'll be, just kind of like you, in the first lab you had to look it up. So you'll look it up for the second lab too. I think it's given in the third lab. It's 10 times, or it's 30 times 10 to the 6th. But the elastic modulus, if you're using that in a calculation, if it's not given in the handout, then you can look it up. Are you talking about the second lab?
Yeah, second lab, sorry.
Okay, yeah, that should be, you'll basically look that up to use it. Kind of like you did for the first lab for some calculations.
Oh, okay, thank you.
Mm-hmm. Okay, so let me pull this up here. So I'm just going to show you an example for making a legend first, and also for fully saving your figures. Okay, so yeah, I'm surprised we didn't go over how to make a legend, because we made this graph here on the first data reduction that we did as a class, and usually I would show you guys how to make a legend here. So you see here, we have 3 curves, and I don't specify which curve corresponds to which material, and you want to know that, right? So I'm going to go in here and make a legend. So I'm just going to go right here. Let's do that. Alright, so looking at this code here, we first plotted aluminum, and then we plotted steel 1018, and then we plotted steel 1045. So that order, it matters. And that's basically what we're going to be using as our arguments for the legend. So to make a legend, all you have to do is type in legend. And then in parentheses, you're going to put, all of the labels that you want inside of your legend. So the first argument, we're going to put aluminum, because again, we plotted aluminum first. So I'll say aluminum 6061 T6. And then the second one is the second plot that we made, which was 1018 steel. So we're going to go with apostrophes again and do 1018 steel. And then the last one is 1045 steel. Alright, so that's all we have to do. I'll run this again. And now, in our plot, we're going to have a legend. So you want to make sure that the legend isn't blocking any of these curves. So like it's not, on top of a curve. And you can move this around wherever you want as well. Alright, so that's how you do that. And then for fully saving your figures, I want to talk about that too. Some of you took screenshots of the screen, which is, understandable. And I even saw a few where you guys took a picture of your actual screen. So I want you to actually save the figure inside of MATLAB. So to do that, this is going to pop up for your figure once you run your script. And then you go to File, Export Setup, and then we're gonna click on Rendering here, and this is just something I do every time. I'm gonna change the resolution to 300. That's dots per inch, and that'll be a nice high quality image basically. Then we're gonna click on Export, and by default, it says a MATLAB figure.fig. That's this kind of format in here that you could open up inside of MATLAB. But we want to have an extension or file format for our report, right? So we're going to go in here, and you can do something like a PNG or a JPEG, or even better, you can save it as an SVG, which is a scalable vector graphic, which is it's a vector graphic, so it's very, very high quality. But you can just do .png, and I don't know. I'm just gonna call it stress strain 3 curves, whatever, and then we'll save that. All right, and then you have basically that graph. Let's open this up. So it's gonna save in the same kind of directory that your script is in. So you see my script is here, and then here's the figure that we have, and it looks like this. So it's nice and high quality. So then you can put that in your memo and it looks, real nice. Okay, so that's that. And we're going to be going over some more things today, more coding techniques that'll help out, with, of course, this lab and then other labs as well. Okay, so let's go over the lab for the beam. So I'm going to go to VKS once again. I couldn't find a really good video for this lab, unfortunately, so unless I find one sometime today, we're just going to go through VKS, which I know isn't ideal. Ideally, you would actually do the lab, of course, but we can't. Okay, so I'm going to go to the beam. I hate that sound. It's so loud. Okay, so I know we went over this a bit last time, but now we're going to do a little more in depth for our very kind of sad pseudo lab here. So this is the beam that we have for this lab. It's an I-beam, if you remember. We have the cross section that we kind of went over last time, so it just looks like an eye. And this is what the entire beam looks like. So I think I can't really tell from this picture, but it's like a foot long. And we're going to apply 2 loads on this beam. But before we show the loading, we have a strain gauge, which is, kind of adhered to this beam. And basically that's going to be on the bottom surface once we actually start to run the experiment. I'm going to post these deliverables later today. But this is the cross section that we have, right? So this is what the beam looks like from a side view. Okay, let's just tuck that away. All right, so here's the beam again. And basically, I actually also want to mention that in the actual experiment, basically I would give you a little cross section of this beam. So it'd be like a really small piece of an I-beam basically. And you would then measure it with these kind of different dimensions here that I give you. And then you would use those measurements to calculate the moment of inertia. But there's an issue there, which I'm kind of, telling you now, so you can write this in your memo for the discussion. There's an issue with that being that the cross-section that you're given, that's not what you're using for the actual experiment, right? So the dimensions that you just measured, they're different than the I-beam that you're using for the actual experiment. So there's already a source of error there because it's an entirely different, material that you're actually using. It's the same material, but it's a different actual specimen, basically. So that's going to be a source of error. Okay. And yeah, it's not symmetric, so basically the measurements that I give you, you're going to be calculating the average for some parts, which we're going to be going over today in the script. Alright, so we're using our friend here, the MTS Insight Tensile Testing Machine. Of course, we have a different setup here, so we can actually apply 2 different loads on this for the beam. Alright, so this is what it looks like. We have 2 rollers here, and then we would kind of put the beam down like this. I say luckily for you, it's automatically set up already by the lab technician, but again, we're not doing it in person, right? So let's see if we got a better picture of the beam kind of set up here. There's not really any good picture showing the setup. It kind of sucks. You can kind of see it here, so imagine that it's totally set up here, and then we have these 2 loads that are being applied to the beam. Let me pull up our handout again. Oh, that's actually in here. Give me a sec. Okay, so we have these 2 loads here. They're kind of in the center, and from these 2 loads, you can see that the beam is going to deflect with this little dashed line here. And in the very center of the beam, you see that we have this maximum deflection. So that's something that we're going to record in this lab, is this deflection here. We're going to record that with a dial gauge experimentally. And also where this max deflection occurs, that's going to be where we have the maximum bending stress for this experiment as well. And we're going to be measuring that and then also calculating it theoretically as well. So to calculate this experimentally, we're going to be basically use the formula where our bending stress is going to be equal to the elastic modulus, which again is given, and I think for this, we're using steel here, and the elastic modulus is, if I remember right, 30 times 10 to the 6th psi, and we're going to take that and multiply that by the strain that we have for this, and we're using a strain gauge again, so we're given that strain directly. Right, so we're going to be calculating that maximum bending stress that we have right here in the center on this bottom surface. Let's put that away too. Alright, so one of the software that we're going to be using again is TestWorks 4. That's to record the loading that we have on here. So basically you would zero out the load, basically what you see here on the screen. I know some of this is pretty abstract because you haven't actually done it, but this is kind of the procedure that we do. We zero all of the stuff out, and we would apply a little preload as well. Alright, so we apply a very small preload. Alright, here's the old dial gauge. I hated using this. Luckily, it's upgraded now to a digital dial gauge that tells you it with no effort at all. And you see that there's kind of a little nub, for lack of a better word, on the very bottom of this beam, and it's in the center as well. So because it's in the very center of the beam, we're going to record that maximum vertical deflection. Here's our better image here. Alright, and then also the strain gauge is down here as well. Alright, there's lab view. Remember, lab view is what we use to read the strain that the strain gauge is measuring. Okay, I guess that's it. I really wish there was some better pictures. So I'll try to look for a video again today. I couldn't find any good ones last night, but this isn't a great. There aren't as many good pictures as I thought there was gonna be. So I guess it's a little lacking in detail, I guess. But are there any questions on the experiment that I can answer now? Okay. Alright, so then I guess we're gonna start with the data reduction. So you can open up MATLAB. Oh yeah, actually I need to first mention I uploaded the data as well, so I'll actually use the same data as you right now, so we can go through that together. So if you have MATLAB open right now and you want to go through this with me in real time, you can do that. So to get the data, go to this week's page, so we're on the home page. We'll go to this week, and then I have the data available right here. So you can click on that, and then you can download it. So I'll give you like a minute to download this right now. It's basically an Excel file. So this time I actually made the Excel file for all of you, because I know last time, for the last experiment, it was in a Word doc, and you could either kind of make a matrix in MATLAB, or you could have kind of made a text file, or you could have put everything in an Excel file like this. But this time I did it for you. Alright, so download this, and then we'll go over the data reduction together. Basically what we're given here is the load. So that's, remember that was with TestWorks 4. It's kind of recorded in there. And we have, what is this, 15 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great guess I had. Okay, so we have 10 points here. We're going up to about 1,000 pounds, so we're staying within the elastic range. And we also have the microstrain that's in, this time it's in units of inch per inch actually, so we're not gonna, we actually will do a conversion again, I believe. I have the script, so we'll look at that. But this microstrain, oh, it's in microstrain, right? So, yeah, I don't know why I said that. So it's in microstrain, but we have to do a conversion once again. And remember that this was recorded in LabVIEW. And then the last column that we have is the deflection, and that's in units of inches. And this was recorded with the dial gauge. Remember, this deflection is that maximum deflection that we have, that vertical deflection we have for the beam. Okay, so I'm gonna stop sharing my screen really quick. So make sure you download this right now and put it in a directory that, that's good for you. I'm gonna get my script real quick, and I'm gonna open it on my other computer. I should have done this before. So give me a minute. Okay. Sorry about that. It's opening up now. Okay. I'm gonna open up the chat on my computer here. Come on, Zoom. Alright, so I know you see this little ugly box, right? That's just the chat, so ignore that. I hate how it shows that kind of box though. It's very distracting. Okay, so I'm gonna make a new script. So make sure you're in a folder that makes sense to you. And make sure that folder has the data that you just downloaded as well. So to make a new script, remember we go up in the top left here and we click on new script. Alright, let me reset my color scheme as well. Just because maybe that's a little, I don't know, distracting to you too. Let me change this to, okay. Alright, here we go. So you see I have the data over here on the left, so make sure that whatever directory that you're in, you have the data over here as well. Oh, sorry, hold on. My entire script didn't open up. It has like one line. Hold on, I need to upload this again. Sorry guys, give me another minute. That's weird. Yeah, this is really weird. I think I'll open it up in just my Google Drive, I guess. Why is it doing this? Oh, it's so weird. Even in my Google Drive, if I open it up on this computer that I'm currently on, it shows the entire code, but on my laptop it only shows like 9 lines. Really weird. Alright, so I guess it's okay. I'll just kind of tuck away my script in one corner. Just because I want to make sure that I cover everything. Alright, sorry for the weirdness. That's very strange. It only shows basically all of the code to when I import the data, and that's it. you see on this computer, it shows all of my code here, but on my laptop, it only shows to this line here. Okay, let me go back to MATLAB. Okay, so, this is the script here, so I'm just going to tuck it away too. So, don't pay too much attention to that. Alright, so we have, let's make our new script. So, let me clear this too. Alright, so we're making our script now. Again, sorry about the weirdness, right? But here we go. EGME 306A. We're doing the beam. Yeah, I'm just really confused why it doesn't show even my entire script in Google Drive, right? It shows it on my one computer, but not my laptop. Really weird. Alright, so we're going to start out this script by clearing the memory. Back when you guys took 205, if your instructor didn't talk about it, which hopefully they did, this first line here, clear, this clears everything that we have in our workspace over here. So I know this was from lab 1 right now. And basically, this line here is going to clear everything out of there. It's going to clear the entire memory, basically. And then this line here, CLC, that clears any text that I have in the command window down here. So when I run this now, all of this is going to go away and all of this is going to go away. We'll need to first save the file. Alright, and then you see all of that goes away and then all of this goes away as well. Alright. So now we're going to import our data. So the file that we have here, it's an Excel file again, and there's actually 3 sheets that we have for it. Let me open this up again. I should have kept it open. Alright, so this is what the Excel file looks like. So you see down here we have 3 different sheets. So I have one sheet called T1 for test 1, and then I have another called T2, and then another called T3. So these are all 3 tests that we have for this experiment. So you're going to have 3 graphs, and on each of these graphs you're going to have a curve for the experimental curve, so what we calculate theoretically. And then you're also going to have an experimental curve for our experimental data. Alright, so we need to import all of those 3 sheets. So we're going to be doing something a little different than we did before to import this data. So what I'll first do, I'll make a comment, and we're just going to basically import the Excel sheet itself, but after we do that, we have to import all of those specific sheets that we have for that Excel data. So I'll make a comment here called file to import. And we're just going to give this basically a variable name, a file name. And what I have this Excel file called was Sue_team1. I got this data from Dr. Sue, if it's not clear. .xlsx. So whatever you named your file when you downloaded it, just be sure to put that in right here. Alright, so what this does is it basically imports our file, but it's still not fully imported. You see right here it says it's a 1x22 character, so we haven't really actually imported it quite yet. All we did is we told MATLAB this is what my file is called. Alright, so we're gonna make another comment here called ops, which is basically this is just kind of like another I guess placeholder, for lack of a better word, for what we're going to use to actually we're going to use this to basically help us import all of our sheets. So we're going to make another variable called ops equals, and then we're going to be using a command called detect import options. And then for the argument, we're going to put file name. So also make sure that you have the capitalization the same here, because that matters. I know it's really weird capitalization. Who knows why? But this is the function we're using, and we're using this function on this argument called file name, which is the file that we're importing. And basically MATLAB uses this function to determine what import options it can use for this file, for this Excel file in this case. I know it's kind of weird stuff so far. I have actually never used this function until yesterday when I was doing this data reduction. You can do it in different ways too, of course, but this is what we're doing right now. Okay, so now we actually have to import all of the sheets. So remember, we have 3 sheets for those 3 different tests that we ran. Okay, so for this, we're actually going to use a for loop. So, throw back again to your MATLAB class. We're going to be using a for loop here to basically loop through each sheet that we have in this Excel sheet. So I'm going to do for S, that's our index variable that we have. So for S equals 1 to 3, because we have 3 sheets. And then I'm going to do ops.sheet. And basically this is, we're looking at this variable here, which remember is used to look at all of the import options that are available for our Excel file. So you see over here, ops is a 1-by-1 spreadsheet import options. So you see these are all of the options that MATLAB tells us that we have for this Excel file. And one of the properties that we have is sheet. So that's what we're basically specifying down here in this for loop. So we have ops.sheet equals S. So this is telling MATLAB that basically that we have 3 sheets for this Excel file. Okay, and then we're going to do so there's 2 things we can do. For one of our import options, we can basically make a cell array, which would basically have a table for each sheet that we have. So I'll show you this way first. So we're going to do T of S. So T, this is going to be the cell array that we're making, and we're going to have S amount of tables. So we're going to have 3 tables. This will make more sense once we actually run this code right now. So we're going to use our read table function that we used the last time. And then we're going to say that we want to read the file for file name, which remember is our Excel file. And then our other argument here is going to be ops, and that was for detect import options up here. So if I run this right now, let me end the for loop as well. I should have suppressed the output. So if I run this, you see that we have a 1-by-3 cell array. Let's open it up. And this is what we have. So basically, it imported every sheet. This is sheet 1, this is sheet 2, and sheet 3. And I can open one up. So this is test 1. And we have all of the data for test 1 in here. And then I could open it up for test 2. We have all of that data. And then I could do it for test 3 as well. So that's one method, but I'm actually going to instead use a different method, just because that's what I did last night. And basically this is going to be a multi-dimensional array. Don't worry, this is the most complicated part actually for this entire script, so don't freak out too much. I know it's a little weird so far if it's been a while. So I'm going to call this X. This is going to be the multi-dimensional array that we have. Why did I call it X? I don't know. I just did last night. Alright, so basically, so far what we have here is X. That's the multi-dimensional array that we are creating right now. And this colon here means I want to take all of the rows that we have for each sheet in our Excel sheet. And this colon here means I want to take all of the columns. So basically we're saying take all of the data for each sheet. And then this last argument S means basically how many layers we have in our multi-dimensional array. Again, this will make more sense once we actually do this right now. So to make this multi-dimensional array, it has to be arrays that we're creating here. So we can't use a table this time. So instead of read table, we're going to do read matrix. And we're going to be doing file name and then a comma ops. Alright, let me make a little comment here. So this is going to create a cell array. And this one here is going to create a multi-dimensional array. So remember, these are just two different options that we have. But for right now, I'm going to use this option here. But you can use the cell array if you want. Alright, so let's run this now. And then if I open this up, you see that we have a multi-dimensional array here. Let's see if I can make it look... I made it look worse. Okay. It's not displaying how I would like it, but whatever. This is one matrix that we have here. So we have 3 columns. Here's our second one, and then here's our third. So basically we have all 3 sheets once again. Alright, making sense so far? Again, this is probably the most complicated part of this entire script, so don't freak out too much. Alright, so we got all of our data. And now we're going to define some knowns. Alright, so the first thing is the length. So this is the length of the beam. Remember, it was 12 inches. So I'm going to say L equals 12. Length of beam, and that's in units of inches. Next one is A equals 4. So this is, remember, we have 3 sections to the beam. We had like A, B, and C. And each of those sections are 4 inches. And we'll be using this later on to calculate the moment of inertia. Or actually, sorry, to calculate the moment. Okay, so we have A equals 4. And this will be section length. And that's in units of inches once again. Alright, B, let me call this base actually. So the base, this is just the base of the beam. And we were given some data that from Dr. Su again. But for this, we'll actually just do as a class because the dimensions that the students recorded, it was in the Word doc that you guys don't have. So we're just going to do it now. But basically what I did is I calculated the average base length. So basically the length, the average length of the top part and then the bottom part. Okay, so we have 1/2 multiplied by 0.993 plus 0.979. Alright, and that's just getting the average base length. And we have units of inches once again. Alright, next one we have the actual height of the I-beam. And from this is for multiple measurements. So we have 0.24 plus 0.489 plus 0.241. Alright, and this is the height of our beam and units of inches once again. Alright, so here are the measurements. I just want to show you guys. So basically, for the height, we're taking this measurement here, plus this measurement here, plus this one here. Okay, then we have D, that's going to be equal to 0.489, and D, okay. Let me open them up again. So I banished my deliverables handout. So D is this measurement here. Okay, so 0.489. Alright, so right there, you can see here 0.489. Next one we have S. Let's go back here. So S is going to be this measurement here. You see the measurements that we have from Dr. Su. That measurement S wasn't explicitly given, so we're going to calculate that. Basically, it's going to be our base here. Where am I? Yeah, here we are. So it's going to be the base minus 0.184. So minus this section here, and we want to get this measurement S, right? So we have to divide that by 2. So again, we're taking this base measurement, we are subtracting this inner measurement here, and because we want to get, you know, basically one side, we have to divide it by 2. Okay, so we have the base. I need to type in base minus 0.184, and then divide it by 2. And I don't know what to call this, so I'm just saying inches. It's kind of a weird little measurement. Alright, next one we have y, and y is going to be the distance from the neutral axis. And remember, the neutral axis, for our case, it coincides with the centroid. So lucky us. So basically that's just going to be the height of our beam divided by 2. Alright, so there we go. Distance from neutral axis. Alright, now we have the elastic modulus, so that's 30 times 10 to the 6th. And that's in units of psi. And then one more thing we have is the bending moment. Alright, so we have m. And for this, we're actually going to already calculate this from our multidimensional array. Okay, so we're gonna reference our multidimensional array, which is X, and we want to get all of the rows in the first column, and we want to do this for every single array that we have. And then we multiply it by our sectional length, which is A, and then we divide that by 2. So let's open this up. The way it's displayed here is really bothering me again too. I think it's because of my personal setup. It's not, you know, putting all the columns across here. But that's okay. Remember our first column here, this corresponds to the load. We have the load in the first column. Now just to make this a little clear, I'm going to open up the table. So we have the load here, and this is the strain from the strain gauge, and then we have the deflection from the dial gauge. Alright, so the bending moment, remember we have an equation for that, so that's the load multiplied by the sectional length, which is A, and then we divide that by 2. So that formula, that was something that we went over in the lecture last time, and I also give you that on the deliverables handout too, just for easy reference. So we want to calculate this bending moment for basically for all of these rows, because we are increasing the load, and because of that we're changing the bending moment. And we want to get this bending moment also for each test that we have. So weird, but whatever. So we're doing this for each test that we have as well. So we're getting all of the rows for the load, and then we want to do it for each test. Alright, so that's the bending moment. Any questions on that part? Okay. This is going to be our load, and then multiplied by our sectional length, so that's going to be pound force times inches. Okay, And now we can start to do some calculations. Alright, and then after our calculations, we're going to do our plotting, so not too bad. Okay, so calculations. First one we are going to do is the moment of inertia. So our moment of inertia, let's go to our deliverables handout, is this equation here. So this equation that I gave you on the deliverables handout and in our lecture last time, basically to calculate this, we're first calculating the moment of inertia for this kind of big rectangle here. But for our geometry, we have to subtract the moment of inertia from these little two rectangles here because, you know, they aren't part of our geometry. So to do that, basically we're just calculating this big moment of inertia and subtracting these two little rectangles. Alright, and then we defined all of these measurements in the section that we just did. Alright, so we'll do I equals 1 divided by 12 times the base times the height cubed. So that's our basic equation for the moment of inertia of a rectangle. And then we're going to subtract those two small rectangles. So minus 2 times 1 divided by 12 times s times d cubed. And this has inches or units of inches to the fourth. Alright, everyone good so far? Is it making sense so far?
Yeah, we're good.
Okay. Alright, next one we're going to calculate some theoretical stuff. So we have the theoretical vertical deflection. And for that, yeah, right here, we have that equation is 23 times P, which is the load, times the length of our beam to the third, divided by 1,296 times the elastic modulus times the moment of inertia. Okay, so we're going to do deflection theoretical equals 23. I'm just going to type this out first and then I'll explain it. Times L to the third divided by 1,296 times E times I. Units of inches. Okay, so we have 23 multiplied by the load. So remember, we do 23 times P times L cubed. So right here is the load. Remember, our load is the first column that we have. So let's open this up. So it's this first column. I'm just showing you this table because it's easier to show you guys visually, but it's the same thing in our multidimensional array. We're getting this first column here. Alright, so we're getting all of the rows in that first column, and we have a colon in this third argument here so we can get every single layer of this multidimensional array. So this is kind of layer 1, that's for the first test, and we have layer 2 for the second test, and layer 3 for the third test. Alright, and then we have the elastic modulus here, which we defined up here, and then we have the moment of inertia, which we just calculated. Alright, so if we run this and we open up our theoretical deflection, then here we go. We have, this is also a multidimensional array that we just created, but it's our theoretical deflection for the first test, for the second, and then for the third. Alright, next thing we have is the theoretical bending stress. Theoretical bending stress. So I'll call this bend stress theo. And for this, we have our moment multiplied by y. So remember, y is the distance from the neutral axis, and then divided by the moment of inertia. Alright, so that's this equation right here. Alright, so we already calculated the moment, and we already calculated y, and we already calculated the moment of inertia. So we're just going to plug all of those in here. So we have m times y divided by I. If we run this, let me go here. Then again, we have a multidimensional array for the theoretical bending stress. So we have a layer for each test. And this will be, of course, units of PSI. Alright, we got, I guess, just one more calculation, right? Yep. So we have experimental bending stress. And down here, I'll say experimental. You know what? I'm going to rearrange this stuff a little bit. Do experimental vertical deflection. Just going to make a comment. We already have this data that was in our Excel file. That was the third column. So we'll say third column from given data, just so we remember that. Okay, experimental bending stress. So remember, the experimental bending stress is going to be our elastic modulus multiplied by the strain that was given from our strain gauge, and that's the second column in our data. So bend stress experimental is going to be E, our elastic modulus, multiplied by, we want to get all of the rows in our second column, and we want to do this for all of the tests. So I'm going to put in a colon once again. And we had units of microstrain. So we want to convert that by doing times 10 to the -6 to get consistent units here with our theoretical bending stress. And we're going to do units of PSI. So now if we run this, and let's look at both of our bending stresses that we just calculated. Put this over here. You can see that they're somewhat similar. So both of these again are in units of PSI. And what we're going to do now is make our plots where we're going to have we have 6 plots in total, right? We have we're going to be plotting the vertical deflection for our 3 runs, and we're going to have the experimental vertical deflection and our theoretical vertical deflection. So that'll be 3 plots there, and then our other 3 plots are going to be for the theoretical bending stress and the experimental bending stress. And I didn't say this, but it's for deflection versus load, and then stress versus load. Okay, everyone good?
Yeah, looks good.
Okay. So, we could do the really tedious thing of having code for 6 plots. That sucks. So we're not going to do that. We're going to use a loop once again. It'll make things easier for us. Alright, so I was first going to show you kind of doing some plots one at a time, but no one wants to do that. So we'll just use a for loop instead. So let me do this. Plotting. Okay, first section here, we're gonna plot the deflection versus load. Okay, so yeah, for this data reduction, I guess I'm kind of showing you everything, but in the last 3 experiments, I'm not going to give you everything for the data reduction, just because I want you guys to kind of think through some of the stuff on your own. I know we're using MATLAB, so and not everyone loves MATLAB, I know. So I'm going to give you most of it, but not all of it, because again, I want you to think of how to do some of the stuff on your own, because even though this isn't, you know, a MATLAB class or anything, think kind of going through the motions yourself of thinking how to do this data reduction is important, right? Because, you know, in your future you might be given some data, and as an engineer you're gonna have to break that data down and then interpret it yourself. But again, I'm not gonna have you do anything, you know, difficult. I'm gonna help you guys out. All right, so we're gonna use a for loop once again.
Okay.
So,
I have a question. So you know how we do the X and then we do double dot and then 2. Does that take in account only like the column for the second column?
Right.
Oh, okay, I see. Thank
you. Yeah, so this is getting, let me open this up here. So this syntax right here, let me highlight it. This is referencing our multidimensional array X, which you can see on the right here. And the first argument is rows. So we have a colon, which means to get all of the rows. And then our second argument is 2, which is the second column, like you just said. So that's going to get all of the rows in the second column. And then the last argument is basically the layer for the multidimensional array. And we have a colon again, which means to get all of the layers. So we're getting all of, we're basically getting column 2 for every layer. So this column, this one, and this one.
Oh, okay. If we were to have 4 of them, would we have to do like a 4?
If you had 4 columns, yeah. Or yeah, if you had 4 columns, if you still just wanted the second column, it would still just be 2 here.
Oh, I see. Okay. Okay, thank you.
Okay, so so for plotting now, we're going to use a for loop again, like I was saying. So we're going to do for I equals 1 to 3. So I'm doing 1 to 3 because, you know, again, we're doing 3 plots here. And I'm going to also put this in here right now. So the first thing I'll do, I'm not sure if we talked about this before, but basically I'm going to put figure, visible, and I'll do on right now. And basically, this is going to run all of our code. It's going to make our plot, and it's going to display all of the figures that we're about to create. And, you know, later I can change this to off, and that'll still generate the plot, but it's not going to actually show us that plot. Basically, you know, once we start doing the other plots and we run them, I don't want to have 6 figures come up at once, so I can basically disable this. So anyways, we want to make our plot now. Remember, it's deflection versus load. So load is going to be basically our first argument, which is x. It's going to be our independent variable. So load, remember that was the first column for the data that we have. So we're going to put our multidimensional array x. I want to get all of the rows in that first column so we can get load. And I want to do this for each test that we have. So I'm going to put I. So this is going to loop through. And so on our first loop, we're going to get the first test basically. And we'll make a plot for that. We're going to loop through again. That'll be for the second test. We'll make a plot for that. And then we'll loop through that last time. And we'll get that third plot. Alright, so just to be clear again, we're getting this load for each test. So this first column. Alright, so that's our load. And now we want to get our deflection. So right now we're doing the experimental plot. So our deflection was also given in our data. That's the third column. Alright, so we're going to get all of the rows in the third column. And we want to do it for each test. Alright, here we go. So if I just run this right now, I should go like this. Okay. I'm going to close out of this. So if I run this right now, then we get all of our 3 plots here. So this corresponds to all 3 tests that we have. Okay, and personally what I do is I also change the line width. I always think the line width by default is too thin, so I'm going to do 1.5, and basically that just makes them thicker. Alright, and we're going to call, I'm going to put a comment here called experimental. Okay, but for each plot that we have, remember we want to have both the theoretical curve and the experimental curve. So right now we need to also add that curve for the theoretical portion. So if we want to have 2 curves on one figure, we need to use the hold on command, which we talked about for the first lab. Right, and now we're going to make our plot for the theoretical stuff. So we're still going to be plotting load for the independent variable. So we're still going to have plot x, colon, comma, 1, comma, I. Alright, that's our load. And now we want to plot or put in the values for the theoretical deflection. Okay, so we're going to put def underscore theo. That's what we made earlier, which you can see over here in the workspace. And remember that was also a multi-dimensional array. So we have def theo, and I want to get all of the rows, and this time I want to get all of the columns because we just have one column, and then I want to get each test, so I put comma I. So we're getting all of the rows. We only have one column, so we say, okay, get every column, which of course is just one, and then we want to get each test. Theoretical, and then we're going to say hold off because we're done. And now if I run this, what did I do wrong here? Did I miss a parentheses? Maybe, yeah, right here. Okay, there we go. So now if I run this, we have both of our curves, and we have it for every single trial as well. So on your screen, you should see like figure 1 and figure 2, figure 3. Maybe you don't. Yeah, actually, let me know. Do you guys see like figure 1, figure 2, figure 3? Like, does it actually say figure 1?
No, not that I could see.
Okay.
It doesn't look like any of them are labeled.
Okay. So I will update you for that because, you know, right now it's looping through and it's showing us all of the plots right away. But we need to, you know, actually know which test corresponds to which plot. And I didn't do that last night. So I'll basically update you on that because we want to, again, display which plot corresponds to which test. And right now, we actually could just do one loop at a time, and then we could know, but I want to make it a little more automated, so.
For mine, it does show figure 1, 2, and 3.
Yes.
Okay. Okay, that's good. Yeah, if you can see that, then you know that figure 1, of course, is going to be for test 1 and so on. But still, I'll update you guys. Basically what I want to do, and there should be a way to do this, is have our title basically automatically tell us or show which test we did. So anyways, I'll do that later on. So first thing we want to do is also add a legend because we have 2 curves here. So I'll do legend. The first thing that we plotted was the experimental plot. So we're going to say experimental. And then the second one is going to be theoretical. Alright, and then I'm also going to specify the location. So if I run this now, you see that our legend, it overlaps with our curves, which we don't want to do. So, you know, we can move this around by ourselves if we want, but we can also just say where we want to put the legend. So I'll say location, and then I'll do northwest. Alright, and then we'll do our labels. I'll do X label, load. Okay, and I'm going to use well, first I'll do this. Okay, pound force. We run that, and then we get our X label down here, but I want to make it look a bit nicer. Not sure again if we ever talked about this in this class for LaTeX formatting. It might have been in my other class, I'm not sure, but I want to make this look a bit better. So personally, I would recommend that you do this. You don't have to, but it looks better in my opinion. So I'm going to put $2 and basically what we're going to be doing now is writing LaTeX code, which if you guys don't use LaTeX, it's like Microsoft Word. It's just a different typesetting program. Anyways, so we're pretending that we're writing LaTeX code right now, and these $signs, they stand for math mode in LaTeX. So within these $signs, I'll put 2 parentheses, and I'll do pound force. So pound, do an underscore, and then put an F, and basically this F is going to be a subscript now. And then we have to tell MATLAB to interpret that as LaTeX code, so we do interpreter. Interpreter, and then LaTeX. Alright, so now if I run this, we get this nice pretty looking X label. And then we'll do this for the Y label as well. So vertical deflection, and that's in units of inches. Okay, and then we do interpreter, LaTeX. Alright, and then we'll add in a title, and then we'll do vertical deflection versus load. And so this is basically what I was talking about before, where I want to have MATLAB basically automatically say, okay, I'm on loop 1, so that means that this is going to be test 1. I'm on loop 2, that means test 2. So there should be a way to do this, but basically we have to use like special functions to convert, basically in this case, convert our test run to a string. So again, there should be a way to do this, and once I find out, I'll update you guys. Or if you just know, I know some of you can see it says figure 1, figure 2, and figure 3. So you already know in that case which test run it is, and you could put in your caption in your document which test run it is based on that info. So that's good too. And in that case, you don't even need a title here. We can just have a caption in our memo, and we don't need to have a title on the actual figure, because basically your caption would say the same thing. It would say, vertical deflection versus load test 1. And I would actually personally recommend that. But if you want a title on your figure, this is what you do. So here we go, and then we have our title. I forgot to put this in parentheses. Okay, any questions on this part? Alright, if not, then we're on the very last part here, which is going to be doing the same thing for plotting, but this time for bending stress versus load. So it's going to be very similar to what we just did, but of course, this time we're going to be doing it for bending stress. So actually, just to save time, right, I'm going to copy and paste what we have here. And now all we have to do is change these, our dependent variables that we plotted, to be the bending stress. So I'll do bend underscore stress experimental, and we want to get all of the rows, all of the columns, it's one column, and we want to get all of the tests. So let's open this up. So that's a multidimensional array that we calculated earlier. So it's the same thing like with the theoretical vertical deflection. We calculated this and it resulted in another multidimensional array. So we get all of the rows, all of the columns, that's one column, and we want to get all of the tests. Right, and then we'll do this also for the theoretical bending stress. So bend, stress, theo. All we have to do, real nice. And then we just need to change our y label here to say bending stress. And now we want to have, units of PSI. So again, I'm going to use LaTeX formatting here. So we have pound force in the numerator and then inches squared in the denominator. So for this, we need to have kind of big parentheses. So I have to do \left parentheses and then \frac. We have two curly braces here. And then we have \right parentheses over here. So now we're going to go into fraction. We have pound force in the numerator and then inches squared in the denominator. And if I run this now, let's change this as well. I'm going to change our title. We have bending stress versus load. Alright, let's run that. Oh yeah, see, we have 6 plots that come up. I don't want to see all 6, right? I just want to see the bending stress plots. Oh god. I closed out of MATLAB too. Alright, let me open this back up. So I only want to see the bending stress plots. So to do that, I'm going to scroll down here and I'm going to change visible on to visible off for the deflection versus load plots. So now if I run this, it'll just show us the 3 plots for the bending stress plots. Alright, and then there we go. So you see these plots, they aren't as close. They're somewhat close, but they really start to deviate as we increase the loading for the experimental versus the theoretical curve. So this will be something that you talk about in your memo as well, and you'll kind of think about why this might be the case, and you'll really expand upon this in your discussion and conclusion. And oh, I forgot to say, for your first memo, some of you, not too many, but some of you didn't have interpretations for the results that you presented. So, in this case, we have 3 figures. So personally, I would recommend show all 3 figures, and then you should have interpretations for those 3 figures as a whole. So you can talk about how it's close in the beginning, and then it deviates towards the end as we increase the loading. And so you'll comment on this, and you can even briefly mention why this might be, but you're really going to expand upon that in your discussion section. Okay, so there we go. Yeah, I thought one of those lines looked a little different. I want to make this line width 1.5 as well, just so they're consistent. Alright, now they look better. Alright, so that's all 3 plots, right? So there we go. That's it for this data reduction then. So, we spent more time on the data reduction than the lab, I know. Because it's virtual this year, I want to spend more time on the data reduction to, put more emphasis on that, because this is still very important stuff here for going through the data that you collected in a lab, because you still need to have the skills to take that data and break it down and process it so you can then interpret it and then discuss it in your lab report or memo, whatever it may be. So yeah, I didn't have a great video that I found, so that's why we're going to go over a video for this lab like we did for the first one. But hopefully the VKS walkthrough that we did in the beginning gave you an idea of what we were going to do in the lab. It's pretty simple, right? We just have our beam, apply 2 loads on it, it goes down, we get our maximum deflection in the center of the beam, and that maximum deflection is going to also correspond to that maximum bending stress on the beam. And so we calculate that bending stress experimentally and also theoretically, and then we compare those plots. And we do the same thing with the vertical deflection, that maximum vertical deflection in the center of the beam. We got that experimentally with the dial gauge, and then we calculated it theoretically as well, and then we compared them. Okay, and deliverables, I'll post them now, right after class, and then your memo is due in 2 weeks for this one. That's, I'm checking the date. That's March 22nd. So this memo is due March 22nd by 11:59 p.m. Memo 2, remember that's due tonight by 11:59 p.m. So make sure that you look at my feedback for Memo 1. Implement that feedback into Memo 2 and all the rest. And that should really help you out. Okay, so yeah, that's it for today. So if you guys have any questions, stick around. If you don't, then that's all I have, so you're free to go. And I'll see you guys next week for the lecture for the column. Alright, so have a good day.
Thank you.
Thanks.
Have a good day.
Thanks, you too.